Okay, so welcome comrades to today's meeting of the Oxford Communist Corresponding Society. Everybody knows the procedure, so I'm not going to describe it again. The talk today is going to be given by Ian, and it's on thought, being, computation, or thought, being, and computation. Ian.
Thank you. Okay, when mathematicians claim that something is true, they point to a proof. And a proof is just a very good argument that begins with premises, which are called axioms, and it takes the form of a sequence of logical inferences, and the conclusion is typically called a theorem. And every step of the proof should be free from ambiguity or any intersubjective disagreement, because the proof aspires to objective truth. So if you agree that the axioms and the rules of inference are true, then you should also agree that the theorem is true. And therefore the theorem, once established, is true forever. And well, at least that's the aim. But the mathematics of the 19th century didn't meet that high standards. So the proofs were a mixture of ad hoc notation and natural language, and often with crucial steps just skipped. So they were too much like ordinary arguments, the kind that people don't agree about. So mathematicians invented formal axiomatic systems to make their proofs entirely rigorous. And a formal axiomatic system, some of you may know, defines a formal language with its own syntax, its own allowed rules of inference, and starting axioms. And a formal system essentially looks a lot like a computer programming language, but in the 19th century, that didn't exist. So today there are lots and lots of different formal axiomatic systems, but some of them are considered foundational. And one of those is first order logic, and that captures logically sound reasoning. Another is Peano arithmetic, which is named after its inventor. And Peano arithmetic, it extends first order logic by introducing things like whole numbers and analogues of addition and multiplication. And it has 9 axioms which state really obvious things like 0 doesn't come after any other number, and really simple things like that. And then mathematicians can prove theorems using the formal language of Peano arithmetic. And so the formal system is a tool that guarantees that every step of the argument is truth-preserving in a sense. And so the conclusion, the final theorem, has this logical necessity. And the proof, so once it's discovered in this language, then it can be seen by everyone to simply result from the mechanical application of the rules of the formal language, rules that everyone can agree with. So that seems very good. Mathematicians, by reflecting on their own practice, partly automated in the form of useful tools, conceptual tools, these things, their own practice, and this is what formal axiomatic systems are. But finding the interesting theorems still requires human ingenuity, because the interesting theorems are like treasure hiding in this vast branching labyrinth of possible inferences you could apply at any intermediate step of reasoning. So this automation was only partial. Now Leibniz in the 17th century, he built one of the earliest mechanical calculators, and he dreamt of a mechanical device that could discover all mathematical truths. And in the 1920s, David Hilbert, the mathematician, he challenged other mathematicians to find a mechanical procedure that, given a candidate theorem, would decide whether it was true or false. But the notion of a computer and our modern understanding of an algorithm didn't exist in the 1920s. So what Hilbert meant, or what anyone meant, by a mechanical procedure was unclear. And there were examples, of course, cooking recipes, if we follow them, if they're sufficiently detailed and we follow them properly, they can guarantee a good result. 300 BC, Euclid's algorithm to find the greatest common divisor of two numbers. educated people at the time obviously knew algorithms for multiplying and dividing numbers. But all these examples of mechanical procedures were also informal, written in everyday language, had ambiguity. So mathematicians had an intuitive idea of an algorithm, but no one knew what the basic elements of algorithms were, or even if there are any basic elements common to all algorithms at all. So they needed to find the essence of what they were doing when they, in quotes, computed something, when they followed a mechanical procedure. And this is what Alan Turing achieved in his 1936 paper on computable numbers with an application to the decision problem. And the decision problem in the title is a name for Hilbert's problem to find an algorithm that could automatically decide the truth of any candidate theorem. And in this paper, Turing reflected on the nature of human computation. And he thought, well, it obviously involves a computer, but at this stage of intellectual history, computer denoted a human thinker who was computing something, say the square root of 2 to 3 decimal places. And Turing noted that computers, that's human computers, they typically use pen and paper. They think, they write down an intermediate result, such as the first decimal digit. They read what they've just written, they think some more, then they write a second digit, and so on, until that computation is complete, when the final answer is written down on the paper. So Turing then introduced some mighty abstractions to get at the essence of this human activity. He proposed that the paper was a serial tape split into equally sized cells that contained either a blank, a 0, or a 1. He assumed that the tape was potentially infinitely long, so there's always enough space to write down intermediate results. And then he entirely mechanized the human computer. He distilled the human into the simplest possible machine that could compute. His mechanical computer had very limited senses, right? So it read only one cell at a time, it had very limited actions. It only wrote to a single cell, it moved left or right to a new cell, or it halted the computation. And the computer's thinking was extremely simple. It had finite memory and a single big, well, small or big, any size, finite lookup table, which specified which action to perform for all combinations of what could be in the current cell and what could be in its memory. And so with those big abstractions, Turing defined what he called his automatic machines, which we now call Turing machines. Now there's an infinity of different Turing machines, and they compute different things according to their lookup tables that control their behavior. And that is an unimaginable variety of mechanical behaviors. So some machines will compute the square root of 2, others compute the square root of any number encoded as input on the tape, others might multiply whole numbers, integers, and so on. In fact, every program that exists today is a Turing machine. So Turing then realized that the machines themselves can be encoded as zeros and ones on the tape. So Turing machines can take as input descriptions of other Turing machines. And this is the point where Turing discovered that some machines are very special, because given a description of another machine, they can behave just like it. Turing called these special machines universal because they can simulate the behavior of any other Turing machine. So formal axiomatic systems are conceptual tools that we can use, but Turing machines are a bit different because they're a closed feedback loop that once started can run without human intervention. And Turing's theoretical breakthrough therefore rapidly merged with technological advances in electronic logic gates, memory stores, and things like that. And so the universal Turing machine became a technological reality quite quickly. And we now live in a world full of non-human computers, and the term computer itself means only that. And the universal Turing machine now exists as a technological artifact in the pockets of billions of people around the world. So it's hard to overstate the importance of the invention of the Turing machine and the universal computer, and its full significance we've yet to fully understand. But in the 1930s, Turing and others were more narrowly concerned with mathematics. So Turing now had a mechanical model of human computation, and so he naturally wondered if these machines had limitations, were there things that they couldn't possibly compute. So at this point, if you want to take a look at that diagram on the handout there, Turing assumed there was a machine, let's call it the solver, that's the grey box in the middle. It can take as input two things, a description of any Turing machine and some input for it. The solver then analyzes the input it's given and decides whether the described machine will eventually halt on that input. So in a sense, it solves a halting problem for the machine that's described as input to it. Will this machine halt on this input? Yes or no? Turing then defined a second machine. I'm going to call it the contradictor for reasons that will become clear in a moment. So the contradictor is another single Turing machine that happens to contain the solver as a submachine. It kind of like calls it as a subroutine. But it has some additional logic. If the solver outputs yes, indicating that the described machine halts, then the contradictor decides to enter into an infinite loop. But if the solver outputs no, indicating the described machine does not halt, then the contradictor decides to halt. So the contradictor simply does the opposite of what the solver says. So then Turing did something self-referential. He encoded the contradictor machine as a description on its own tape, and then he fed all that input to itself. So Turing asked the contradictor to analyze its own behavior. And the question then is, what will happen? Well, if the contradictor machine in fact halts, then when analyzing its own behavior using the solver, it won't halt. And conversely, if the contradictor doesn't halt, and when it analyzes its own behavior, it will halt. But that's complete nonsense. Because the same machine cannot behave differently on the same input. So Turing had derived a logical contradiction. He had assumed that a solver machine exists that solves a halting problem for any other machine. That implies that a contradictor machine can exist, but as we've just seen, it can't. And therefore, the original assumption that a solver exists cannot be true. Obviously, his proof was more technical than that, but that's the gist of it. So Turing had proved that no Turing machine can solve the halting problem. It's an impossible computation. Now, all Turing machines eventually halt or continue forever. So there are an infinity of facts of the matter. But no single Turing machine, doesn't matter how complicated it is, cannot produce all those facts. Turing machines can solve special cases of the halting problem. They might solve it for a finite subset of other machines, but no Turing machine can solve all the cases because they themselves will fail to halt on some inputs. Now this proof, Turing's proof, revealed the existence of something very important, which is now called computational undecidability. A decidable problem always yields a clear yes or a no, a true or false answer, but undecidability introduces a third possible answer, which is undecidable or I don't know. True and false are therefore insufficient. We need a third truth value, which is neither true or false. And since Turing discovered undecidability, we now have loads more examples of undecidable problems. In fact, Turing immediately found another one in his 1936 paper. So Turing applied undecidability to Hilbert's decision problem. So let's consider an unproven conjecture in number theory. So Goldbach's conjecture, which is quite famous, states that every even number greater than 2 is the sum of two prime numbers. Today, no one knows if that is true or false. We can define a Turing machine, that's a computer program, that exhaustively generates every statement derivable from the axioms and inference rules of Peano arithmetic. Now that naive algorithm, just described, just mindlessly generating all the possibilities, should stop with the answer yes if it finds Goldbach's conjecture, or no if it finds the negation of the conjecture. And then that Turing machine we just described would be like immensely powerful, because it could solve not only Goldbach's conjecture, but any unproven conjecture in number theory. Just feed it as input a different conjecture, yes or no. We wouldn't therefore need any creative leaps to solve every mathematical problem. We just simply ask the machine to prove or disprove a conjecture and just wait, patiently wait for it to give us an answer. And that machine would solve Hilbert's decision problem. But Turing proved that no machine, however sophisticated, can actually do that. And the reason is that some formal systems, such as Peano arithmetic, they're sufficiently expressive that they can describe Turing machines and their behavior. So in other words, Peano arithmetic can simulate Turing machines. So Turing translated the halting problem into the language of Peano arithmetic. He constructed a special statement in number theory that asserts that a Turing machine of a given description will halt on some input. And this statement, it turns out, is provable in Peano arithmetic if and only if that Turing machine in fact halts. Now, if that statement was in fact provable, then we immediately would have an algorithm that solves the halting problem, because we could just mechanically apply the axioms and inference rules of Peano arithmetic to prove whether any machine halts. But we already know that no algorithm can possibly exist to do that. So Turing derived another contradiction, and it implies that this special number theoretic statement can't be proved in Peano arithmetic, even though it's true. And that means that some arithmetic truths are not decidable by the formal system called Peano arithmetic. So, for example, it's possible that Goldbach's conjecture is undecidable in Peano arithmetic, and therefore that naive algorithm we just described, it wouldn't work, because it might never generate Goldbach's conjecture, just print out more and more statements and never halt. Now, that doesn't mean that the naive algorithm or even really sophisticated algorithms are useless, because we have automatic theorem provers and they're really useful, but they can only prove some truths of arithmetic. It doesn't matter how sophisticated they get, they can't prove all number theoretic truths. Even algorithms that make creative leaps by inventing new kinds of formal axiomatic systems can't prove all the truths of arithmetic. So these impossibility proofs at the foundations of mathematics are quite stupendous. They have really far-reaching consequences, and the link to Gödel's closely related results incompleteness theorems, very, very closely related. They're just kind of the minor variations of each other, to be honest. These results were very surprising at the time. But now, much later, we actually see that undecidability is absolutely everywhere in mathematics. Just take some examples. It's undecidable whether two integer matrices can be multiplied together in some sequence to yield a zero matrix. Can't decide that in general. Don't know. Diophantine equations, these are polynomial equations that must have whole number solutions. So you can write them down, loads of variables, that's an equation. Can we solve them in general? No, we can't. It's undecidable solving Diophantine equations. There's loads more examples like that. But undecidability also appears in the material world of actual computers. So deciding if an arbitrary program will stop, or how long it will take to run, or how much memory it will need, or how much power it will consume, those are all undecidable problems. Deciding if an arbitrary program correctly satisfies a logical specification, or if two arbitrary programs perform the same computation, or whether a program is as small as it could be, that's all undecidable problems as well. And there's loads more. Now, we can always partially solve undecidable problems by finding new algorithms to solve special cases, and that's really useful. But undecidable problems will never yield general solutions. So Turing's paper was justifiably celebrated. It formalized the concept of a mechanical procedure in the form of Turing machines, demonstrated that no Turing machine could solve Hilbert's problem, and revealed the existence of this phenomenon called undecidability. But all those results depended and do depend on a deeper premise, which I want to now turn to. And that deeper premise is called the Church-Turing thesis. And that's the proposition that Turing machines really do capture our informal, intuitive idea of human computation. That it really is the case that every conceivable mechanical procedure is a Turing machine. That we cannot conceive of algorithms that are not Turing computable. And therefore what humans can possibly compute and what Turing machines can possibly compute is identical. Because if that Church-Turing thesis was false, then it's possible that one day we might find an algorithm that solves Hilbert's decision problem, even though the algorithm cannot be executed by a Turing machine. So there are lots of reasons to believe that the Church-Turing thesis is true. So early pioneers of computability theory, they proposed very different models of what it means to compute. Church had the lambda calculus, Gödel and Kleene had recursive functions, Imel Post invented string rewriting and tag machines. These are all very different, sort of mechanically specified systems. They're quite different. But everyone quickly realized that all those different models are computationally equivalent to Turing machines and vice versa. So everything that can be computed in one model can be computed in the other. And it's only because Turing machines very closely model sort of mathematical thinking, human thinking, that that model became canonical. It could have been any of the others. So this phenomenon of computational equivalence suggests that underneath a variety of all these models, all of which have elements of complete arbitrariness, there's a single phenomenon underneath called computation. And today, we now know there's like a huge array of simple mechanisms that are computationally universal and therefore equivalent to universal Turing machines. I mean, it's endless, but register machines, cellular automata, molecular reaction networks, systems of differential equations, neural networks, on and on and on. Universal Turing computability arises very easily from simple mechanical components. And they all can simulate each other, all those kinds of things. And even multiple interacting Turing machines that read and write on a single tape in parallel, that's computationally equivalent to a single Turing machine that sequentially simulates each of the submachines and their parallelism. Another reason to believe the Church-Turing thesis is that since it was proposed over 80 years ago, no one's discovered a new effective model of computation that exceeds their power. But the Church-Turing thesis isn't a mathematical theorem. It's not a priori truth. It's a scientific hypothesis because it could be refuted. So I think it's significant that at the foundations of mathematics, we face an open question rather than an axiomatic starting point. Now, since the Church-Turing thesis was first formulated, as we mentioned, computation is everywhere. So now it's seen as too narrow. So people like Zuse, who's one of the pioneers of computation, built one of the earliest computers, Deutsch, the physicist, Wolfram, the physicist and computer scientist, lots of other people, they propose more general versions of the thesis, which is sometimes called the physical Church-Turing thesis, but I want to call it here the computability thesis. So the computability thesis states that everything is computationally equivalent to a Turing machine. So Turing machines can compute anything in nature and vice versa. Now, we don't know whether nature is fundamentally discrete or continuous, but we do know that any continuous system that we know can be computed to any degree of accuracy by a Turing machine. So the computability thesis is consistent with the existence of continuity in nature. So from this more general standpoint, The Church-Turing thesis is just a special case, restricted to that part of nature where humans do mathematics. Now, the universe appears to have a speed of light barrier. We can't travel faster than light. According to the computability thesis, the universe also has a Turing barrier. Nothing in nature can solve the halting problem or any equivalent undecidable problem. So we can't prove the computability thesis, but to refute it, we just need to find something with super Turing powers that functions beyond the Turing barrier. So experimental psychologists, they measure what humans' minds do in controlled settings. Good example would be presenting us with two 3D shapes, one a rotation of the other, or maybe not. How quickly we can work out that they are just a rotation of the other one. It's like, press a button when you think you know the answer. Thousands of experiments under that kind of paradigm found no evidence at all that the human brain solves problems in a way that breaks the known laws of computational complexity of the intrinsic problems themselves. All of the areas of science, physics, biology, continually probe what nature does. But despite all that scientific activity, we have no evidence that nature computes in a way that breaks computational laws. And when some theorists have proposed a theory that claims to find uncomputable properties in nature, then other people have come along and said, oh no, it's Turing computable. Gödel's first incompleteness theorem stated that penal arithmetic can't prove all number theoretic truths. And that generalizes to even more powerful axiomatic systems. And Roger Penrose, the physicist, he's argued that because we can prove Gödel's theorem, then our reasoning transcends any formal method. And therefore, he says, our mathematical intuition must be super Turing. But a Turing machine can mechanically prove Gödel's theorem. The proof just happens to prove a limitation of its own method of proof. And the fact that we can do it and machines can do it doesn't imply that either of us are super Turing. Massive investments in chip design, more speculative investments in new kinds of computational media, such as quantum computing and molecular computing, they give no indication that super Turing computation is possible. Quantum computers can be much faster, but they don't compute beyond the Turing barrier. Some theorists have proposed new models of computation that are super Turing, but they typically assume things like infinite computational steps can be performed in finite time. So it's not clear that those models refer to something that could possibly exist. Proposals for relativistic super Turing machines that exploit gravitational time dilation at the edge of black holes, which sounds fantastic in both senses of the word. So perhaps in some distant future we could exploit yet to be discovered super Turing powers in nature. That's possible. It's conceivable that one day a genius will discover a method that exceeds the power of Turing machines. Maybe. But all the evidence so far indicates that subjective human thought and objective nature is at least Turing computable. So deciding the truth of the computability thesis is actually a decision problem for us, and one which we've not been able to decide yet. Now, in computability theory, a semi-decidable problem is one that a Turing machine can always decide when the answer is, say, no. But when it should decide yes, it will sometimes fail to halt. And we can think of our exploration of nature and our attempts to invent new kinds of computing machines as repeatedly asking this question of nature: is nature Turing computable? At any time we might find an empirical counterexample and therefore halt with a decision no. But we can never halt with yes, because we cannot prove that the thesis is true, either mathematically or empirically. And that means that the computability thesis is a semi-decidable problem for us. So most people think that the computability thesis is true, and therefore that Turing barrier can't be breached. But I want to spend just a few moments considering maybe that the computability thesis is false. And in that hypothetical situation, we might be able to breach that Turing barrier either by discovery or by invention. So let's say that one day we discover a mechanism that we suspect is super-Turing. It could be an exotic configuration of matter, it could be alien technology, like in 2001. We feed the mechanism representations of Diophantine equations to solve, and then examine its output. We interact with it. Now, it's easy for us to check whether a solution is correct, even if it's very hard for us to find that solution in the first place. And then we discover that the mechanism solves every equation that we throw at it. But if you think about it, that won't convince us, because finite empirical evidence isn't sufficient. Because from our perspective, we can't rule out the possibility that one day that mechanism will fail to solve an equation. We need a proof that the mechanism solves all Diophantine equations. And the only proof we can get is by understanding precisely how that mechanism works. And there are two possibilities here. If we only have Turing computable powers, then the mechanism will ultimately be unintelligible to us, because we'd be incapable of fully comprehending how it computes. And so we could never know whether it's an infallible super-Turing oracle, which we could reliably consult and get answers, or whether it's an ordinary Turing computable device, which one day will let us down. And as an oracle, it would grant us access to realms beyond the Turing barrier, but because we're not computationally equivalent to it, we wouldn't know it, and we couldn't know it. So the other possibility is that we are computationally equivalent to it, in which case the mechanism will be ultimately intelligible to us, and therefore in principle we can reverse engineer its general method, unlock its super-Turing powers in our own thinking and technology. And then we would have broken through the Turing barrier, and we would know that we had. So that's discovery. If we take it from the other side, which is invention, so instead of discovering, some genius invents a new method for solving Diophantine equations, which they claim is general. And then we feed them arbitrary equations, and they solve all of them that we give them. But again, finite empirical evidence is insufficient. We need proof that their method is truly general. Now, if they can't give us a proof, or we can't reverse engineer their method by examining their brain as they solve equations, then we're again faced with an unintelligible mechanism, except this time the oracle is a fellow human. We'd have access to a super-Turing oracle, but we wouldn't know it and we couldn't know it. But let's say that they do provide proof that their method is general. Now, a mathematical proof. Now, they will need to introduce some new axioms in a sufficiently powerful formal axiomatic system that would need to represent some kind of creative leap by asserting the existence of new kinds of mathematical objects or structures. But mathematical provability isn't identical to truth, because nature might disallow super-Turing computation. So if that's the case, then their proof is just like a counterfactual statement. It says something like, if these assumptions are true, then the proposed method would be general and super-Turing. But if the assumptions can't hold in nature, then that proposed method is just wishful thinking. It's like dreaming of a perpetual motion machine. And we're sort of in that situation right now, because theorists have proposed super-Turing machines and they're given mathematical proofs of their powers, but skepticism is high because there's nothing we can do with those proofs. Can't do anything with them. Their assumptions may not be correct. So we need stronger proof of an empirical nature, not a mathematical nature. We need to realize that general method in practice. We need to make it real. We need to objectify it. We need to actually construct a super-Turing machine. And again, there's two possibilities here. If nature doesn't allow it, we'll fail. Along the way, we might learn why those assumptions cannot hold. And in a sense, that would be an empirical refutation of the proof. But if nature does allow it, then we'll eventually succeed and we'll build a super-Turing machine. We'd actually construct one. And the general method for solving Diophantine equations is equivalent to solving the halting problem. So this new machine would solve all equivalent undecidable problems. We'd know if any Turing machine halts on some input. We'd have new algorithms for generating mathematical truths. We could write computer programs guaranteed to be free from any bugs, and much more power besides. And we would have broken through that Turing barrier, and we'd know it. So there were different possible worlds that we might be in, and I've done them on that sheet there. And in those different possible worlds, the Turing barrier might be hard, it might be semi-permeable, or it might be permeable. But what stands out from the options is that the computability thesis will always appear semi-decidable to us if, 1, it is true, or 2, it's false, but only nature has super Turing powers, or 3, it's false, but only we have super Turing powers. These different possible worlds are indistinguishable for us. We can't tell them apart. But there is a fourth case where we are beyond the Turing barrier because we can construct mechanisms that we know are super Turing, just as today we construct computers that we know are Turing machines. And that is obviously a great leap forward. But it wouldn't be the end of the story, because it turns out that there are degrees of undecidability. Because Turing, in a subsequent 1939 paper, considered computation with the help of external oracles, where an oracle implements an uncomputable function, and we've got no idea how it does it. But he just supposed one exists, an oracle. And oracle machines are, in theory, just in theory, more powerful than Turing machines. But oracle machines have their own halting problem, and they can't solve it. So there are whole classes of problems that still remain undecidable for them. So undecidability still exists beyond the Turing barrier. And some oracle machines are more powerful than others. And in fact, there's an infinite hierarchy of degrees of super Turing computational power, in theory, and a corresponding infinite hierarchy of degrees of undecidability. Some undecidable problems are, in a sense, much more undecidable, much harder to solve than others. So if we did get beyond the Turing barrier, we'd formulate a more general version of the computability thesis, which includes Turing machines as a special case. It would state that everything is computationally equivalent to a super Turing machine, but this more general statement would again be unprovable, although empirically refutable. Because if we just discovered or invented one example of super Turing computation, and we break through the super Turing barrier. But in this new regime, we'd again encounter undecidability, and we would again generalize the computability thesis. So onwards and upwards, as if in a spiral. And if that's on this page here, this flowchart, it shows how our knowledge might evolve or reach kind of stasis, depending on whether we're computationally equivalent to the whole of nature or not. But what stands out there is that at each step along this hypothetical ascent, the corresponding computability thesis is always semi-decidable for us. And so we'd have no way of knowing if we ever reached any limit. And so if this argument is correct, then no matter how many computational barriers we break, or even if we break through none at all, some form of a computability thesis will always appear semi-decidable to us. And that means that the computational equivalence of mind and nature is transcendentally undecidable. We simply can't know whether our computational powers are or are not identical to nature's. For us, that problem is undecidable, and we will not halt on it. So let me come to a close by pointing out some possible implications and things we might want to discuss. So stepping back from all that and thinking about it more broadly, computation is our current theory of what we take our own thinking to be. And if our thinking is computation, then nature, in order to be intelligible to us, must appear in the form of computation. So the concept of computation sort of defines intelligibility. And that's why the computability thesis states that at root, both thought and being are forms of computation. It's a modern restatement of the older philosophical idea of the identity of thought and being. And this might seem very circular and self-referential, simply stating that to be is to be intelligible, and therefore it's philosophically vacuous. And it's no accident that both Gödel and Turing's impossibility proofs, they do employ self-reference, where a system attempts to reason about its own reasoning, to get at the heart of itself. But it's not vacuous, because any version of the computability thesis is empirically refutable. And so it does have content. It circumscribes the limits of what is currently intelligible to us. And it's a limit that we can probe and maybe surpass. And the thesis is open, and so it gives a different kind of answer to the old philosophical question. So my feeling is that computation isn't a naive philosophical monism, whether that be materialist or idealist, because it doesn't dogmatically assert that thought and being are identical. Instead, transcendental undecidability implies that we cannot know that we truly know. But computation is not like the a priori categories that we find in traditional Kantian and post-Kantian philosophy, for two reasons. Computation is more abstract than any category. All known abstract and concrete systems, including the known categories of thought, they're reducible to it. And computation, although it also emerges from thinking about the conditions of possibility of our own thinking, it doesn't imply there's a kind of unknowable residual, like Kant's thing in itself, which leaves us with a noumenal world that we cannot know. Instead, transcendental undecidability implies that we cannot know that we truly cannot know. So on the question of the identity of thought and being, the computational approach answers with the third value, neither a yes or a no, neither a true or a false, but undecidable. We simply can't know either way. And that might not seem very helpful. But even to Socrates, the oracle at Delphi had to explain that knowledge of ignorance is a kind of philosophical progress, because it's precisely because we cannot know the limits of our powers to think being truly that it makes perfect sense to never give up, even when faced with persistent unintelligibility, because what is undecidable today may become decidable tomorrow. Thank you.
Okay, so any direct questions? Go ahead.
Is there a Turing machine that outputs either 0 or 1 genuinely random?
That's an excellent question. And the answer is that's undecidable. And it's linked to Kolmogorov complexity theory, which is a definition of randomness that's intended to be independent of probability theory. And a sequence is considered random if there is no Turing machine that can generate it that is shorter than the sequence itself. And
so what was the name of the theorem?
Russian mathematician Kolmogorov.
Kolmogorov.
Kolmogorov. Kolmogorov.
Yeah, sorry, can you spell it again?
Kolmor.
M-O-G.
Kolmog. I'm probably pronouncing it wrong. And the point being that is a very, very mathematically and philosophically interesting concept. But you can't compute the Kolmogorov complexity of any sequence. So we can't, well, if you have Turing, only Turing powers. So assuming we only have Turing powers, then we can't empirically distinguish between we can't identify a truly random sequence.
Yeah, anybody else with any direct questions? Okay, open that up for discussion. Any comments?
Yeah, do you have a direct question actually around the timing of Turing's thesis and Gödel's thesis? Which came first, and did they know each other, and that's the history of those two?
Yeah, the Gödel incompleteness theorem stuff came first, and they did know each other. Well, yes, they did know each other. I think they met, and certainly they're in the same scientific field together, and Turing's work came afterwards. So Gödel's paper is all about Hilbert's program, right? Decision problem was just one part of it. Hilbert wanted a formal axiomatic system that would be completely consistent, have no contradictions, and it would be good in the sense it would only produce truths of mathematics, and Gödel's proof was that no formal axiomatic system can do that, so that killed one part of the program. But the residual was that, okay, that may not be possible. We could still perhaps have a decision algorithm for format, and that's what Turing then also killed in his paper afterwards, and then the whole thing was dead. But in the process, discovering something of great significance, yeah.
I think you touched on it a bit. Really interesting talking. You mentioned Penrose and sort of theories of consciousness. Just wondering, would you say like consciousness is more than computation, or would it be sort of equivalent to computation? Like, I know Stuart Hameroff, who worked alongside Penrose and trying to derive like theories of consciousness, came up with consciousness kind of is a quantum computation in the brain within these microtubules, which then creates what we call consciousness. But yeah, it'd be interesting to touch on that a bit more.
Yeah, Mike.
Yeah, this goes back a hell of a long way. I remember being taught about Gödel and Turing in sixth form, or rather in what was called upper sixth form, which was...
Year 13, no.
Is it? For what it's worth, I think what we came out with at the end of it was that the inference from this is that you have to be willing to act on uncertain evidence because mathematical certainty, because how shall I put this? The argument, we start with the argument for probabilism, which goes back to John Locke, the critique of probabilism, and not just John Locke, but his contemporaries, and the critique of that, which is offered by Berkeley and Hume, is that can never supply the degree of certainty of mathematics. And that there's a flip side of that, which is the certainty which is supplied by mathematics allows you to be confident that we can never be sufficiently certain of inductive inferences from induction. And because we can never be certain from inferences from induction, we should accept authority. Because you can never be certain of the inferences from induction, but inferences from authority are at least giving us some ground, because the inferences from induction will always be contradictory, therefore there's always going to be a possibility of public disorder. If you allow people to act on inferences from induction, and therefore we have to have Hobbes' sovereign. Okay, I know this is a long way. It's gone a hell of a long way from this stuff, but that was what our guys who were talking to us about in the late 1960s about Gödel and Turing and so on were talking about, was because the problem is that in order for the program of saying that the mathematical materialism more justifiable for us to take decisions on pure logic and mathematics and axiomatic systems than it is on the basis of inductive argument, because the inductive arguments are always incomplete and imperfect and so on. It has to be the case that the mathematical axiomatic systems are capable of being self-standing. And then this stuff, the guy who taught me was arguing, shows us that the mathematical systems can't in fact be self-standing, that at the end of the day, the mathematical systems rest on the same inductive foundations as our claim that we think that the sun will rise tomorrow morning because it's done so every time, etc., etc., etc. And therefore, that the argument that lies behind, which lies behind Berkeley's and Hume's critiques of Locke, and because it lies behind Berkeley's and Hume's critiques of Locke, lies behind Kant's two critiques and Hegel's attempt to escape from Kant's two critiques by way of phenomenology, etc. A whole mass of this fucking stuff. But it has a sort of, and I don't know whether the bloke who taught, whether I'm misremembering what I was taught, or whether the bloke who taught me was going off complete tangent. But it did seem to be at the time that it had politics and epistemology significance to it. That if you reached the conclusion that the logical systems couldn't be self-standing, that had implications. So it's just a comment.
Yeah, Ed.
Yeah, thanks very much, Ian. Very interesting talk. Some way off my home turf, but I'm one of those vulgar monists, so I'm going to have a go at it. It seems to me you are, in your chart with the various options, you're thinking that if nature is not wholly Turing computable, then we'll know it by the fact that it's able to perform hypercomputations like solving the halting problem or whatever of that kind. But there are imaginable systems, a system that contains genuinely continuous values wouldn't necessarily be able to solve the halting problem, but could only be approximated by a discrete computer. So it's, and that's sort of what I was driving at with random numbers as well. I mean, I don't want to, I don't think we want to stake everything philosophically on the current physical model of the universe, because I think theoretical physicists would say that this is a work in progress and the present standard model of particle physics is unlikely to be the final answer. But the orthodox quantum mechanics as we have it now wants there to be genuine randomness. And I think wants there to be continuous mode. Probably we shouldn't stake too much on that, but that's a way in which computation would approximate would be able to approximate the physical world, but that wouldn't necessarily allow allow hypercomputation or whatever. So I think there's another possibility there. And I think, if we're saying that being is a form of computation, which I think you said, then as one of those vulgar materialists, I would much prefer to think that that computation can approximate to but cannot exhaust. The computation is one of the things that being does. But I don't think it can be the universe as in itself. The universe as a whole is not equivalent to a Turing because any machine that you actually construct, as opposed to an abstract, lambda calculus in a book, there are certain facts about it that are not part of the computational output on its test. Turing machine has a physical computer that operates as a Turing machine. Has a mass, it has a colour. It produces a certain amount of heat when it moves its tape, and things like that. Those are not part of, those might be computable by another Turing machine, they might be emulatable by itself, but then it would be describing the properties of the emulated machine. There are brute physical characteristics of the machine that are not encapsulated in the computations that it performs. The only Turing machine of which that's not true is one that's an abstract mathematical concept. The Turing machine in the 1936 paper doesn't have a mass, doesn't have a colour, because it's only an abstract mathematical idea. But a machine that physically exists in the world does have those characteristics that are, I'm not remotely saying uncomputable. I'm not saying that the colour of my laptop is uncomputable, but my laptop doesn't itself compute that colour, and if it stores a picture of itself, then it doesn't know whatever. The picture that came from the manufacturer might well no longer be quite the gleaming plastic. Anyway, so I think if we're saying that being is a form of computation, or that the universe as a whole is equivalent to a Turing machine, then we are saying that the universe as a whole is something abstract and ideal, which I'm not certain we want to. I'm not certain we want to go in that direction. There was one other point that I wanted to make, but I don't now recall off the top of my head what it was. So if other people jump in, then I'll try and remember and come back to myself.
Yeah, well, thanks very much, Ian. I really enjoyed that. I thought it was a superb talk. It reminded me in many places of several parts of The Hitchhiker's Guide to the Galaxy, with people may have seen that and may recall various bits of it. I mean, the Babel fish, or the existence of the Babel fish, being presented as the proof of the non-existence of God, and also building supercomputers to sort of answer the ultimate question. There was that kind of running through my mind all through the talk, thinking, there's so much like those philosophical questions explored in that series. But I was fascinated by the idea of there could be things that are true but not provable, like you talked about Goldbach's conjecture. It's not something that's particularly occurred to me before, to be honest, that something could be completely true, but you can actually kind of, but it may not be provable that it's true. And there's part of me which thinks, well, in that case, in what sense is it true? So I mean, I think that there are questions that are raised about the nature of truth and the nature of proof as well, which are not nowhere. After that talk, I think that these concepts are nowhere near as obvious, self-evident in their meaning as it sounds. Especially if you can prove that something can't be proved. That if something's true, I mean, like, suppose Goldbach's conjecture, I say actually, suppose it turns out to be true. It can't turn out to be true, even if it is true in that sense, if it can't be proved. And am I right in saying that you weren't saying it can't be proved, but it could be that it can't be proved?
Yes.
Yeah. So, to me, that's an extraordinary thought. I believe that the angles in a triangle on a flat surface add up to 180 degrees because it can be proved. But if there are things that are true, I mean, mathematical concepts in mathematics which are ultimately true but can't be proved, then that kind of, to my mind, raises a question of in what sense are they true? What do we mean by proof as well? I mean, the other thing is that suppose we have some kind of supercomputer that proves some mathematical conjecture, but or that it claims to prove some mathematical conjecture, but what it churns out is something like 100,000 pages of dense text, together with however many addressing however many special cases, 2,000 special cases. Nobody would be able to. No human at all would be able to absorb all that and to be able to, after reading that, intuitively see it. So in that sense, in what sense has it been proved? I mean, it may be that if you could take it all in and just hold it in your head all at once, you would then be able to intuitively see it. And that kind of raises another issue. I mean, there's the old saying, isn't there? I don't know where it comes from exactly. Maybe J.B.S. Haldane, I'm not sure, that the universe is not only queerer than we imagine, it's queerer than we can imagine. So it may well be that the mental capacity of human beings is just not high enough not at a high enough level to actually see some of these things. I mean, like a fish. Well, maybe I don't know. As the Taoist philosopher said, I'm not a fish. I don't know what a fish thinks. But one assumes that a cat, for example, can't really understand higher mathematics, no matter how much it's taught, and no matter how true in inverted commas that higher mathematics is, that a cat is not going to be able to see it. I can well believe that there are plenty of things that are true that we are just simply physically, because of constraints on the construction of the human brain, that we just physically can't appreciate. So there was something else as well, but I can't can't remember what else I was going to say. But anybody else?
I guess just arising directly in that, your point, you said, it's already the case that there's a whole mass of stuff which we can't individually keep in our heads, but that we can collectively, as a social group, keep in our heads. And there's a curious aspect of that, which is that the national curriculum has reduced the collective mental capability of younger generations of people, because you've got a fixed set of things which every school child has to learn. There's a whole load of stuff which nobody learns, whereas the older generation, because there wasn't a national curriculum, if you get a whole raft of people together, there's going to be some people who learned Chinese, and some people who learned Arabic, and some people who learned medieval history, and some blah, 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 whatever the hell it is. The national curriculum, on the contrary, has the consequence that everybody learns less, and the net output in terms of the ability to apprehend through the collective apprehension is reduced. But that's I don't think that directly relates to Ian. Well, I suppose it does relate to Ian's point in the sense that the computability issue supposes that we're looking at things which, if it works as axiomatic deductive proof, it's going to command universal assent. So that in consequence, it does have to be individually apprehended rather than something which we can just something we can collectively apprehend without being able to individually apprehend.
Well, yeah, you first, and then Ed.
I have sort of encountered this some 30 years ago, and I find it interesting to see it happen again, that some of these ideas are liberated for people who, certainly in my case, it was more about chaos mathematics, but the idea that things were unknowable, unformulatable, this very much tied into a sort of anarchic state of mind that I was part of. And so to try to bring this talk a little bit towards politics and being, that I found it at that time liberating that the reductionist ideology was not possible, and that was great. But since that time, I've spent my time trying to think of how to build up a society using rules or laws or frameworks. And so I found myself responding to this talk with, I'm not interested in what I can't know, I want to know what we can know. What can we build? Not what can't we build, but what can we build? Then we're finding in our own time, these mathematical ideas are quite a few steps of abstraction away from what we actually do, but there seems to be quite a strong correlation between the AIs and neural networks that we're now creating, where they can give you an answer, they are oracular, but they can't explain themselves, and you won't get the same answer twice. And end on a pun, halt or loop, be still or no. I'm sorry.
So I don't catch that at the end, the pun.
Be still and no is a family motto.
Right. No, I didn't hear it first time yet.
Yes, to Rose, dance.
Yeah. I mean, a lot of these things that you can, that are true but you can't prove, or that are true but that you can't prove, involve self-reference which is a huge theme, really, I suppose, in the 20th century thing. It feels like a trick. But I mean, a statement that we can all say is true, and that you, Z, can know is true, but you can't say, is Z cannot consistently affirm this statement. I can say it, you can know it's true when I say it, but you can't say it out loud because of a self-reference trick. Whether or not computation, in the sense that we're talking about Turing computation, is equivalent to the universe, it's important, I think, to recognise that it really does pick out something that's significant and real. I mean, as Ian mentioned, but I think it needs emphasis how surprising it is that lambda calculus, which seems like an entirely different kind of thing from Turing machines, and which was developed independently, they turn out to identify exactly the same set of problems as being computable and the same as not being. And that's a very that's a very remarkable result, and I think very much strengthens the idea that the intuitive idea of a computable, solvable problem is an intuition of some real category, and that those two formalisms pick out that category. The fact that they both map the same ground is much stronger than either of them mapping it on its own, and then there are further ones. Didn't some string theorist say maybe human beings just aren't clever enough to understand string theory? I wouldn't expect my dog to understand special relativity. But I think that was slightly when the person in question was under pressure for not producing testable predictions. And it feels slightly like a get-out. I think you have to work on the assumption that you want your theories to produce. Anyway, is it a problem? I don't know whether it's a problem. Is it a problem if we are saying that nothing in nature is more than Turing computable? In other words, there are no infinities in nature. There are no non-computable reals in nature. A lot of mathematics turns out not to be talking about anything in the world. And a lot of mathematical proofs rely on the idea of infinity, at least that there's always another integer bigger than the one you're looking at. If the universe is a Turing machine, then either the universe is infinite in space, which I think is not the current cosmological orthodoxy, or there is a biggest integer that the universe can store. Like for your laptop, it doesn't often come up, but notionally there is a number. Integers in it are not like integers in mathematics, because if its whole memory capacity is storing a single number in its binary representation, then there is a largest number that it can store without losing precision and storing an approximation to it. And that would mean that it's not true that you can always have another integer in nature, there is a biggest. I mean, it would be a large number, but it would not be infinity. Now, maybe it's all right to say that mathematical proofs that rely on infinities, which I think even Turing, I might be muddling up Cantor, Gödel and Turing, but I think even Turing uses the diagonalization arguments that, now maybe that's fine and the arguments still work even though there's nothing in nature corresponding to non-computable real numbers, which is very, very overwhelmingly the majority of real numbers in conventional mathematics. It's a different level of infinity from the tiny fiddling little infinity that's the computable real numbers. But what's the status of all those mathematical things if they couldn't be computed by the humans?
Yeah. Okay. So we need to draw to a close because the time's getting close to 9 o'clock. So in a moment, I'm going to ask Ian to respond to whichever of those points he'd like to. You don't have to respond to them all. But before I do that, a couple of announcements. Firstly, next week's meeting is going to be here in this building, not necessarily here in this room. We get told what room we're in when we go in through when we come into the building on a Thursday evening. But next Thursday's meeting is here in this building, and we continue with the theme of the nature of nature, I guess. The title of next week's meeting is Frankenstein and the Politics of Nature. So that's next week. Then that brings us to the end of this 8-week series of talks, and then we have a bit of a break. We have a meeting over the Easter holidays on Thursday the 30th of March. So that's 4 weeks from today, 3 weeks after next week's meeting. And that is not going to be here, that's going to be in the town hall at 7:30, Thursday the 30th of March. And the title of that meeting is Anatoly Lunacharsky, 1875 to 1933, and God building. Okay, so here.
Yeah, thanks, everyone. That was some really, really, really good. All it was really good, very stimulating responses. I like them so much that usually when I record this and I stick it on the web, and normally I cut out all the responses because people don't want to be involved in the recording. I would like to include all the responses in the recording. If anyone objects, just tell me and I'll take it out. If no one objects, if everyone agrees that's okay, then I will include it. If anyone objects, just tell me, I'll take it out.
I have no objection.
Fair enough.
Brilliant. I'll stick it all in then, because I think the comments are just really added. So there's no way I can tackle all those huge themes and questions that were raised. But I'm pleased because I think the talk worked in the way that I hoped it would, because it brings all the philosophical issues should be raised in this context, right? And the political implications. So missing from my talk was any mention of Hegel and any mention of Marx. But really, I think they were there all the time. It's just that the intersection of people that have a decent understanding of computability theory and the people who have a decent understanding of Hegel and Marx, I think is a set of 0, actually. I don't even include myself in it. But I've always thought, and I very much think now after putting this together, that there are similar themes are just arise in new forms, and the theory of computation is a more recent form of a perennial philosophical problem. Now, and it adds something new, I think. So, Tim, I'll start with you, Tim. You're saying about this idea of undecidability is very liberating, right? And I agree. But then you asked, I agree because I'm not suggesting anyone here is this at all, but there are some philosophical approaches that are dogmatic in the sense that they assert that the world is such, it's all matter in motion. It's materialism, or it's all spirit. It's all an ideal thing that's manifesting. And they're kind of mirror opposites in some respects. Materialism of Marx and Engels isn't that, by the way. It's more the recognition that our powers as finite beings are limited compared to everything else, and it's kind of a realism in that sense rather than a materialism is what I'd say. But anyway, slightly off tangent here, and then there's the Humes and arguably Kant, which leads to sort of skeptical conclusions. There's dogmatic thing. The world is like, the universe is like this. There's the skepticism, which is, oh my God, we don't know it at all. We can't possibly know it. And the computational answer is neither of those, right? In fact, when you asked, okay, it's good that I know that we can't know. But the other thing is that we can't know that we can't know. And that's different. And he said, what can we do? And the point of the talk at the end was that we can't know there are any limits. We can't know there are any limits. And therefore there's an asymmetry there immediately, which is if you want to try and do something, there's no reason up front to be skeptical that we can't. Even when something's persistently unintelligible, because it might become intelligible. We don't know that we can't know. And that is liberating, but also leads to a pragmatic approach to these philosophical questions. And I'm going to quote Marx's second thesis on Feuerbach. The question whether objective truth can be attributed to human thinking is not a question of theory, but is a practical question. Man must prove the truth, that is, the reality and power of this sideness of his thinking in practice. The dispute over the reality or non-reality of thinking that is isolated from practice is a purely scholastic question, end quote. And this computational approach is entirely consistent with that, I think. So I find it liberating, but also not leaving us without any way to go. The opposite, really. Right. So let's return to Ed's championing of materialist monism, which I'm sympathetic to. I completely understand, and skepticism about the universe being Turing computable. So the technical point is, continuous systems can only be approximated by Turing machines, but the kicker is to any degree of accuracy. And so for all intents and purposes, they can be approximated to any degree of accuracy that we wish. And you're right to say that we don't know whether nature is fundamentally discrete or continuous. We don't know. But we do know that independently of that question, we wouldn't be able to definitively say that continuity exists if we only have super Turing powers. It's one of those kind of computational barrier issues, right? So as of now, it's not possible, in principle, for us to measure a continuous real number in practice, because it requires infinite computational power. So even if nature was truly continuous, a continuum, it's not clear that if we had super Turing powers, we'd even be able to distinguish that state from a universe which is actually maybe very fine-grained but discrete. And the same goes true for the quantum mechanics and randomness. Now, I think it would be a reasonable thing to say that if we were Turing computable and nature was super Turing somewhere in some places, then we would find patterns in nature that would appear irreducibly random to us. And quantum mechanics appears random to us. But if the argument of my talk is right, we can't deduce from that it in fact is random, because randomness, due to the theory of Kolmogorov complexity, which I didn't have time to talk about, we can't identify true randomness. And it's exactly the same phenomena of undecidability, basically. If there is a Turing barrier for us, we can't know it, because it will always be semi-decidable, that question. And so quantum mechanics might be an example of intrinsic randomness in nature, and therefore undecidable. Or it might not, and it might be decidable tomorrow. So there's no reason to give up. Now, I think Engels sometimes, in his discussions of materialism, which I'm generally fully on board with, sometimes I think he does step into this assertion based, I think, on his reading of Hegel, that thought and being is identical. That it's kind of an established philosophical position. And I think that does sometimes step into, now depending on one's interpretation of Hegel, I'm not a Hegel expert, but depending on one's interpretation of Hegel, that may or may not be the case. And Engels' reading may be incorrect. But I feel that sometimes in some things I've read of Engels, he's gone into that state. And that becomes a kind of dogmatism. He's just saying, it is the case that we're up to the job. And to me, that's not something that can be asserted. It's not scientific, fully scientific. Because we cannot know that we truly know, but neither can we cannot know that we truly cannot know, if you get me. Could the whole universe be a Turing machine? I think it could be. And the worst philosophical argument I can possibly give to that is the Matrix movie. The stuff, all the physical stuff, all the sensuous stuff, the colours and the sounds and that. That's not phenomena like that. Because if you look at a modern computer game, the complexity of it, the ontologies that it can create, is almost as it will be one day as rich, but not quite as rich. But it's rich, and there's no reason to think that arbitrary ontologies could not be implemented ultimately in terms of computation. And if we were things in that machine, if we were sub-machines of that machine, then I mean, it's not clear to me that it wouldn't be pretty hard and physical. And again, this is more philosophical, but if Aristotle, like form of forms, only the philosophical stuff, we're looking at the essence of being. The essence of being can't have any real content. If you think about what we're saying with computation, it's actually a really tricky concept. What is that stuff, computation? It's almost contentless. It does play that functional role in the theory of something that is so abstract. Okay. I will try and. There's quite a lot of things brought up, and if you don't mind, I'll like keep going a bit longer, if that's all right. Or do you want to just give it a rest?
Yeah, I mean, but try to be quick because we do have to leave the room.
Right. I'll just do one last thing then. Let me see. All the Hume, Berkeley stuff, the need for the mathematics is itself maybe a basis, an inductive theory of the world. I think that's all on target. And Hume's skepticism about it's impossible to look at a sequence of data and extract the law of it and then expect that to continue. Well, from the point of view of computability, the opposite is also true. You never look at a sequence of data and assume that it's random. It's undecidable. Is it lawful and going to continue to be lawful? Or is it random and does it continue to be random? We don't know. There's an obverse of Hume's problem of induction that is rarely mentioned, that it becomes clearer when you think in terms of computation. So it has loads and loads. All this stuff has, obviously, everyone knows, has loads and loads of interactions with old philosophical problems. And it's also linked to philosophical issues and the foundations of mathematics. So Zed, you said, how could something be true but unprovable? Well, it's unprovable relative to some assumptions, which are encoded in a formal axiomatic system. But you could mathematicians do. They make other assumptions. There are more powerful axiomatic systems and of the kinds of reasoning, of the kinds of logical inference that people disagree about whether they're valid or not. And one example would be something called transfinite induction. So induction is where you basically say some property is true for an infinite sequence of things. Therefore, it's true for all of them. But then there are some problems where there are degrees of infinity. And you might want to induce some property over higher degrees of infinity, and that's where transfinite induction comes in. And that, in fact, allows you to prove the truth of some conjectures that can't be proved in, say, perennial arithmetic. So you have like a more powerful formal axiomatic system, and then you can prove some things. So there's some theorems of number theory that are proved with such assumptions. And then the question is, well, is it true? And that is an ongoing issue in the philosophy of mathematics right now. There's the continuum hypothesis for set theory, and mathematicians are disagreeing about what set of axioms they should agree on. And at that point, the axioms aren't like sides of a triangle adding up that seem to be intuitively true for everyone. You're actually exploring a space of possibilities and constructing mathematical objects that exist but may not exist. And then therefore the truth is relative. There's different kinds of truth. It's true relative to some assumptions. Do those assumptions hold in reality? Well, we don't know. So I would tend to think of this mathematical exploration as exploration of our imagination to explore what might be the case. But we have to accept the fact, and mathematicians, I think some do and some don't, have to accept the fact that truth isn't a property of provability. It has to be a pragmatic property in terms of, can it be finally realized in something that affects the world that we actually live in. That is where we are with the computability thesis today, and the proposition that everything is true and computable. We don't know whether it's true or not. One day it might prove to be false, in which case we'll be more enlightened and have more powers, or perhaps one day it never will be decided. But my point is that either way, some form of the computability thesis in the future, might be called something different, might be a new kind of theory, will remain undecidable for us in terms of this root question about our computational equivalence between us and nature as a whole. Well, I'll stop. Thanks.